Hi, a hearty good morning to all of you, and I would like to welcome everyone to this free FEM online course for geotechnical engineers. So, today the session will be the fourth one in this series, and we are going to cover the topic of construction stage analysis of 3D tunneling. I am Chinmoy Patnaik, and I will be your host for this session. So what I'm going to do is I will play the recorded video that I had made for the webinar so that we could be more engaged with the participants in here. So what you can do is if you have any questions, please feel free to right away put them down on the questions panel. I'll try to answer the questions to the best of my abilities. So without wasting too much of time of yours, I would like to start the course program right away. So, and I will repeat myself, if you have any questions, again, please feel free to put them down on the questions panel. Thank you very much for participating in the session.
The broadcast is now starting. All attendees are in listen-only mode.
Hi, so let's start with today's session. That will be the construction stage analysis of 3D tunneling. So for the contents of today's session, at first I'll just introduce you to GTS, and in the second part we'll have the background description where I will show you the basic tunnel construction methods that is used worldwide. Then there are some points for TBM tunneling that we will try to cover. In the analysis and output section, we will cover the basic workflow process for a finite element program. We'll describe the model. We'll check the geometric design, the meshing and loading cases. Then we'll see the construction stage planning and the result outputs. So finally, in the end, we will have the certification tasks where we will generate the model and analyze the model stages and the results compilation that you have to finish and submit on due time. So meanwhile, if you have any questions, you can directly post them on the questions panel. We will answer you as we progress through the session. So for the course overview, this online certification course in computational geotechnics will be done using the finite element method platform GTS NX. So here we will introduce you to the salient features of GTS NX that you have been seeing on through the various sessions that we had before and also in this session. And we will show you the power or the usage of the finite element method for civil engineering solutions. Here in this session, we will use the nonlinear static construction stage analysis to depict an accurate representation of the field conditions. And then we will have the FEM result interpretation. And in the end, the certification task will be given to the professionals and graduates in computational geotechnics using MIDAS tools. So we'll start with the theory or the background description for today's session, that is the tunneling methods. So I'll start with the basic tunnel construction methods. So the most used tunnel construction methods are the cut and cover method, the drill and blast method, the TBM method, the sequential excavation or the NATM method, and the jack box method. So we will try to cover the three most used method, that is the DNB or the drilling and blasting, the TBM, and the NATM method. So I'll start with the drilling and blasting method. But before that, we will see what influences the choice of a tunneling method. So this entire slide has been taken from the website called Puzzmeister. You can always go and check it out for any other info that you need for tunneling. So basically, costs are the most important factor, or the project economics are the most important factor, along with urban safety and infrastructure safety for any project. So right now, DNB is still the most cheapest method that is present in the market, and it is also much more faster than the TBM method. So, in terms of differences for DNB or the NATM method in comparison to the TBM, is that in terms of site prep time, DNB takes very less time to prep, and you can directly start with drilling after the survey has been done. But for TBM, there are a lot of things need to be considered, like you have to create a shaft to put down the TBM, and then there is the assembly time for the machine. So these are various factors that influence the prep time for the site. And in terms of excavation rate, TBM can be much more faster than DNB, depending on the type of strata that it is going through. For tunnel shape, DNB is typically a horseshoe shaped, but it can be changed too. TBM is mostly round in shape, and Also, DNB is much more flexible as compared to TBM method in terms of any design changes that have to be incorporated in the middle. So for ground vibrations and urban safety, DNB method is leads to much higher ground vibrations, mainly due to the vibration induced by the blasting force. In TBM, it is quite low, and drilling and blasting method is very critical in the populated areas or urban areas, while TBM can go smoothly under a city, which is actually very common nowadays that every city has been undergoing new subway stations and metro rail lines designs. So TBM is generally the more appropriate method for the urban areas. And in terms of access to skilled labor, for DNB, you need specialized engineers like rock or soil mechanics engineers. Then you need blasting engineers, you need excavation or mucking experts, and you also need scaling experts. You also need to have other experts like routing experts, and these kind of experts that are needed for any site specific problem that is present for any particular construction method using the DNB technique for a tunnel. For TBM, it is mostly pre-assessed what kind of issues they are dealing through, and it only requires, apart from geotechnical engineers, it requires the mechanics which can directly work on the TBM whenever it is stuck or it is in the breakdown or the maintenance time period. And also, the one major difference is that drilling and blasting is a cyclic method. So you have to start and then you have to stop, then you have to prep up and then start. But TBM is a continuous method. That is why TBM is much more taking shape or much more frequently used nowadays. Also, in DNB, the wall profile is not very uniform. So, due to blasting, there might be dislodgement of various rocks or weaker sections of the strata, which is why sometimes we can go ahead with the TBM method depending on the UCS of the bedrock in there. Now, for drilling and blasting tunnels, the method is fairly simple. You start with surveying, then go with drilling, and then go with loading. When I say loading, it means the charging, or you have to load the explosive into the drill holes. Then the blasting is done. Post blasting, the ventilation is required so that the noxious fumes are released to the atmosphere. And then there is mucking. After mucking, there is scaling. Scaling is nothing but whatever loose rocks remain on the tunnel wall or the roof profile, they have to be scaled by the scaler machine. Then we go for supports or the bolting or shortcutting, and then the process repeats for the surveying. So post blasting stage, you can see the ventilation, the mucking, and the scaling. These are what actually slow down the process of the construction. So these are very critical stages or the constraints that are present in the DNB method. They are also present in the NATM method. So these issues are eliminated by the TBM method. Now, in a NATM tunnel, the design philosophy is very simple. The design criteria is rated for NATM technical requirements and also for the external constraints. So for the NATM technical requirements, you have to start with the ground investigation, then the geometry size and the excavation patterns decided, then monitoring supports are put on there. So along with that, the final support and the primary support is installed. In terms of external constraints, the purpose of the tunneling, then the financial issues, the contractual issues like what kind of labor is available locally or what kind of labor you have to get hold of, and then the settlement criteria for that particular section, the environmental impact, then the safety, and also what kind of technology you want to use for the progression of the sequential excavation. In terms of TBM tunneling, the ground is there, and then the TBM normally works in segments. So the on the left, the diagram that you see is what we will try to cover in today's section. So along with the shield and the grout and the segmental lining on the walls, we have various forces that act with the progression of the TBM. That is the drilling pressure or the face pressure. That is the load applied by the cutter on the walls. Then we have the jack thrust, that is the movement of the pistons, so that the machine is always closely related or very close to the cutting section. And the segmental pressure is actually the pressure applied by the surrounding strata on the segments that have been uploaded by the TBM method. So in our model that we're going to cover today, we are not taking into consideration the drilling pressure, the jack thrust, and the segmental pressure, just to keep the model as simple as possible. So I'll start with the methodology. So the workflow process of any finite element program is fairly simple, and it always remains the same for any software that you want to use. You will start with the geometry, where you can create your own geometry or you can import your CAD file. Then you develop your material properties, your element attributes. Then you develop your properties in GTS NX. So where you assign a 3D, 2D, and the 1D property to various things like the soil body or the segmental lining, or let's say you have rock bolts or any beam properties or truss properties. Then we have the mesh. So we have to transfer the geometry into a mesh, which is where the finite element process slowly starts taking into shape. After the mesh is applied, we we apply the loading and the boundary conditions. So either you have static loads, you have dynamic loads, or you have various constraints. Then you come to analysis, or the software computes the problem issue and then it solves it. And finally, it displays the result, where we see the contour map or the graphical output of the various forces acting on that section. Or we can have probes, or we can also develop the reports. So now we'll come to the numerical model design. Our objectives are fairly simple. We start with the geometric design. We'll add the structural elements. Then we'll have the material and meshing properties. We will have the loading, the groundwater, and the boundary conditions. And finally, in the end, we will have the analysis results, and we will try to compare the results if there are different cases. But for this method, there is only one case, so there won't be any comparison. Now I'll start with the model layout and description. So this is how our model is going to look like. The entire solve body you can see is in transparent right here, so that the tunnel and the cross passage inside are visible. So here we had tried to simulate the TBM excavation in soil layer, where the main tunnel or the bigger tunnel, the main tunnel diameter is 5.6 meter. Then we have a cross passage that is 3 meter dia, and the depth from ground is 22 meters. The total length of the main tunnel is 50 meters, and the progression length is around 2 meters for each segment. For the support system, we have concrete lining. So the entire main tunnel and the cross passage have the concrete lining of 25 centimeters thickness, except on the intersection area or this area. So this is where the stresses will be higher. That is why here the concrete lining is of 50 centimeter in thickness. And for the loading conditions, we have only applied the gravity or the self-loading condition. So I hope the model design is clear for all of you. Now we'll start with the geometric modeling. So this is how the geometry will look like. Again, the soil body is made in transparent, so that the inner solids are visible. So these solids have been divided into 25 segments on the main tunnel, and on the cross passage, just near the intersection, the cross passage is progressing at an advancement rate of 0.5 meter, and after a distance is reached of around 2 to 3 meters from the main intersection, then the cross passage starts going up at the segmental length of 1 to 2 meter each. So for geometric modeling, it is nothing but creation of point, lines, and intersections. Then we create 2D faces. Then we'll create the solids and start with the Boolean operations. And finally, the geometry will be transferred to the finite element model that will look like this. So this is the complete model that is incorporated with the loading cases for the self weight and also the boundary conditions. So for loading and the boundary condition, we'll just have the self weight or the gravity. And if you want, you can also have the groundwater layer assigned in there. And then we assign the boundary conditions. That is the fixed and the roller boundaries. So as I described that this model will have the construction stage method because this is a segmental process. So we will have to proceed with the construction stage method. So I'll just play this small video where you can see how the model construction stages are planned. We will cover this more thoroughly in the model itself. So each excavation stage is proceeded with the activation of the lining in there. And now for the results. This GIF shows the animation of the total displacement that happened in the final stage from starting of the first excavation to the end of the cross passage. So the total displacement is around 2.346 centimeters, which is quite low. And in results, we'll have the membrane force acting on the shell element. The shell or the shotcrete lining is nothing but a 2D plane shear element. So here we can get the force results, that is the for the horizontal and the vertical forces. The output is on kilonewtons per meter. Then we also have the bending moments. They look like this. And in terms of results export, you can actually export the result data into graph. So the graph on your left is nothing but the graph from the displacements. And in the end, you can also, if you want, you can also export your model data or any result that you want in a Word format or a JPEG or a PNG format. So this is all that is for the interpretation of the results. Now coming to the certification task. So for the certification task, you have to create the 3D tunnel and the cross passage geometry. Then you have to create the analysis cases for the construction stage method. You have to generate, if you want, you can generate images for the 3D PDF report in the output. And then the annexure will be provided to you, which were also done in the previous cases. And please note that the submission date is 21st May. So just like last time, we want to introduce some guidelines that you will be provided by mail the submission link, and only the submission that have been done via the link will be accepted. Mail submissions will not be accepted. The model data and the task files along with the installation files will be provided to you via mail on 12th May, that is tomorrow, and the last date for submission will be 21st May. So meanwhile, between that, if you have any doubts, you can always contact us as at globalsupport.midasyuser.com. We'll be very happy to receive your mail. So right now, that is all for the PPT I have. Now we will start with the model. I'm gonna start with the basic idea behind this model. Then I'll show you how to build it ground up. So right now we are having this in the isometric view. So what we're gonna do is I'm going to switch off the grid. So this is how your model is going to look like when you finish the geometric part. The outer solid is the soil, or if I want to make it transparent, what you can do is just click on the solid. The first will be left click, then a right click, then go to transparency, make it transparent. So when I make it transparent, you can see all the segments inside. So the bigger segments are for the main tunnel, and the smaller segments are for the cross passage. And this being the intersection of both. So that is what we will try to cover in here. Now, what I'm going to do is I'm just going to hide the main solid. So if you want to see the distance between the start and the end panel, what you can do is go to the connection or the measurement tool. Just click on this point and click on this point. You'll see the distance noted as 50 meters. So that is the total length of the main tunnel. Similarly, for the length of the cross passage, it will be around 12.6 meters. So you can always take a note on how to use the measurement tool. So in the measurement tool, you can also measure the distance between a point and an edge on a plane, or a point and a face, or between two edges or two faces, and also the angle between 3 points can be determined by using the measurement tool. This tool will come in handy for you if you are unsure about how to like what is the total length or what is the dimension of your particular solid or from here till the end. And for the cross section or the cross passage, the segments look like this until the cross passage is closer to the main tunnel. That is where the segments have been made slower in length, because we do not since this is the area where the most of the stresses will be concentrated. That is why the rate of advancement is quite low, and it is only possible to increase the rate of advancement after certain advancement has been reached. So if I again use the measurement tool, you'll be able to see that the first advancement is of zero point 0.6 meters, second one is of 0.5, and the third is also 0.5 meters. So until a total length of 1.6 meters has been reached, only then we start with the normal advancement rate of 1.5 meters. Okay, and then it is reached to 2 meters. But this is for the display model. The tutorial file that you will get, it will not have advancements like this, because again, we don't want to make your task very complicated. Instead, what we intend to see is that how much can you accomplish with this particular numerical file or numerical model between the given time period. Here we are not there to test your we are not here to test your skills in numerical modeling. So please understand that. And with that, we'll proceed towards the meshing phase. So this is how the mesh is going to look like. So if I go to basic here and I select mesh set, I can activate and deactivate the meshes on my own requirement. So I just hide it right now. And this is how the mesh set is going to look like. So if the tunnel, the main tunnel panels look like this as shown here, first, second, third, and then slowly we go towards the end. So there are 25 panels for the main tunnel. Similarly, there will be 25 mesh sets for the tunnel lining, because each panel will be supported by the subsequent lining. As I have mentioned in that PPT, that the lining will be 25 centimeters thick, except the lining around this part. This is where the lining will be thicker. Now, so after this, the loading stage here will be just only gravity. So if I go to analysis tab and I go to static load, so we have only applied the gravity based loading. We have not considered the various forces like the drilling pressure, the face pressure, the jack thrust have not been considered in here. And then there is the boundary condition. So when I say boundary condition, it means nothing but having fixed boundaries in the bottom on three sides and allowing the sides of the 3D structure to move in one direction or two directions based on the constraint given to it. But don't worry, for this, even for this 3D model, the auto constraint will work. So you don't need to assign any boundary condition manually. Then we come towards the material models. Here, the good thing is we don't have a lot of materials. The soil has been taken as linearly isotropic and homogeneous in composition. So it's just a basic Moore Coulomb model with an elastic modulus of 50 MPa and Poisson's ratio of 0.3, dry unit weight of 20, and the KO determination has been done automatically. Don't, if you have your manual data, you can do that. Otherwise, The KO determination will be done by the software using the formula Poisson's ratio by 1 minus Poisson's ratio. Then for the porous tab, we have the saturated unit weight as 21 kilonewtons per cube. And in the nonlinear tab, we have taken the cohesion of 30 kPa and the friction angle of 26 degrees. So that is for the soil parameter. And then we come to the concrete material. The concrete has a strength of around the concrete has a strength of around 27.3 GPa, the Poisson's ratio of 0.2, and a dry unit weight of 24 kilonewtons per cube. Now, after this, let's close it down. Then we go to the property tab. So in the property tab here, unlike the models that or the topics that were covered before, which were 2D topics, now we are dealing with a 3D topic. So for the participants who had participated in the previous sessions, they remember that the diaphragm walls have been modeled as a beam element, but for a 3D model, you have to model them as a shell element. Some softwares or some platforms call it as a plate element. So both of them work in the same exact engineering method possible. So here, what you're going to do is you start with the soil property. It's nothing but a 3D solid property. So to create, press 3D, and I just name it as the soil, let's say. And for material, we just choose soil and we press OK. So if I press soil 1 and I press soil in here and I press OK. So that is how you create a 3D property. Now for a 2D property, you just go to this lining and shell. So for this creating shell properties, you go to create 2D, then we go to shell. Here we name it as lining 1. And the material property will be concrete because that is the material normally taken for the shotcrete. Or even for the concrete lining, they don't differ too much. Only the difference is that the final concrete lining has a bit more high strength than the shotcrete preliminary lining. So here the uniform, we have taken that this plate or the shell is of uniform thickness, and for the main tunnel lining, the thickness of 25 centimeters, and we press apply. And for the intersection, I just name it as interlining underscore 1. Same property goes there for the material concrete, and everything remains the same except the thickness is taken as 0.5 meters or 50 centimeters, and we press OK. So this is how you can create properties. But again, I just displayed it in the model here. You will also get the detailed description of how to create property on the tutorial that will be provided tomorrow. So after that is done, I'll just show you briefly the analysis cases or the construction stage analysis. So to replicate that clearly, what I'm going to do is I'm going to deactivate uh, I'm going to deactivate the main soil layer. I will repeat myself again. For any technical questions that you have for this particular model, please keep them for the end. I'll try to answer them to the best of my abilities. If you have any technical question, then please keep them for the end. For any other questions regarding licensing or the progression of the sessions, please feel free to ask them. My colleague will take care of those questions. Okay, so thank you very much for your cooperation. Now, I have switched off the soil mesh set so that the tunnels and the linings and the intersections and the cross passages are visible to all of you. Now, I just go to the construction stage planning. So I use the pan option and take it to the extreme right. And I start with the initial stage. So in the initial stage, the main soil body and all the tunnel segments are there except the lining segments. So all the mesh sets except the lining is activated in here. And please note that for this model, we have not taken interface or groundwater level into account. One can debate interface would have given a bit different result, and that is true. but for the sake of simplicity, we have not considered that. Also, this is quite a big model. So with the creation of interfaces, it might be difficult for the participants to interpret and do it properly with the certification task, because it is indeed a hectic job. So that is why please note that we have not taken interface in here. Now, after the initial stage, you see that we just activate the lining and deactivate the tunnel segment. So similarly, that is how we keep on doing it. So if I just rotate it a bit. So for the stage one, we deactivate the first stage, and then the stage two, the main tunnel lining of second part is activated and the second segment is deactivated. For stage three is the same. It keeps on going until the entire tunnel has been excavated, or the main tunnel has been excavated. Only after that we start dealing with the cross passage. So since there are 25 segments, there are 25 stages for the uh, main tunnel excavation. Now we start with the cross passage. So this is the first lining that is activated, and that particular section is deactivated. So if I'm gonna hide the tunnel methods and only keep on the cross passage methods visible, it will be a bit clear for all of you. So I'm gonna hide it now. So now you can see clearly how the progression of the cross passage construction takes place. 1, 2, 3, 4, 5, 6, 7. So 25 plus 8, that means we have 33 stages in here, and that is how we will design the construction stage method. So I hope the basic geometric design and the mesh sets and the construction stage planning was clear for all of you. So now I will start with creating the geometry for you. So to create the geometry, I just go to here. So first thing we do, just like every other tutorial that has been provided to you, is change the grid size. So it's 2 meter right now, that is fine for us. So we press OK. Now we go to the front view and we create a circle in the origin. So we select the location point of the circle. Before that, just click on make face, click on the origin. In the radius tab, enter 5.6 and press apply. So here you can see it is created now. So the cross passage center is located around 25 centimeters from the, 25 meters from the origin in the y direction. But to create something on the y direction, we also have to change the orientation of the work plane. So to accomplish that, we click on the move work plane tab. We select the y-axis work plane. We press OK. So if I go to right view, now we are working on the YZ plane. So in terms of center location, I put it as 0 and 25. Press apply. With the radius being 3 meters, make face apply. It can be either done that way, or you can directly just click on here, location, and you can enter the radius as 3 meters. Okay. So I'm going to delete the previously made circle. So this is where we have it. This is the cross passage. This is the main tunnel. So what I'm going to do is I'll just move the cross passage to the X direction. So go to translate, target object, direction x-axis, method will be move, distance will be 12 meters or 20 meters, whatever will be given. I am taking as 20 meters and I press apply. So there it is. So now we will start with creating the 3D surfaces. So for to do that, I'm gonna move the work plane again. But before moving the work plane, I'll just try to extrude this one. So I go to protrude, extrude, select the 2D face, direction, x-axis, length will be -20. One, if you want to know why it is -20, because we are moving in the negative x direction. So press apply. So there you have it. So similarly, before going there, what I'm going to do is I'm going to create a cutting plane. So cutting plane is nothing but a 2D plane that can be of any shape, but the shape should be bigger than the solid that you plan to cut. So that is the main or the only critical concept behind the cutting plane option. So now what you do is we again use a translate option. Select this one, direction, x-axis. Instead of move, we select copy, distance, point, uh, distance, let's say it's around 2 meters times 20. Sorry, times 10. So this is how it's going to look like. We press apply. Okay. And then I just delete this one and this one. So one part is complete for us. So what I'm going to do is right now, I'm going to just cut the solid. So I go to solid divide, target solid, select the tools in here. I delete the original solid and also the tool. Press OK. So here you can see we have the segmental increment in here of 2 meters each. Now I go to 3D for the main tunnel. So for the main tunnel, what I do is again go to extrude, select this, direction Y, length. Let's say I take it as 80 meters. The view. I think 80 meters will be too long, so I take 50 meters. That looks fine to us. I press OK. So now what I do is I again move the work plane because we have to work on the XZ plane right now. So I select this, go to this front view, OK. Then I press it like this. So now I just go to solid and I deactivate all the solids except this one. All the solids we just recently created. And I also hide the face. Now similarly, we're going to create cutting planes for this one. So I select this rectangle. Before creating it, I select the make face option and my cutting plane is complete. Now I just switch off the grid for a better view. So to do that, what I do is I'm going to again use the translate option. Click, direction, Y, copy, distance, 2 meters times 25. Okay. So there you have it. So this is how you can create the cutting planes. Now, before working with the cutting planes, I am just gonna hide them. So just hide them. So I am only left with the solid, and I just switch off the solid and activate all the solids. So here you see it. This is how this entire solid appear. Okay. Now what I do is I'm going to deactivate all the solids, only activate this solid, activate the surfaces. Then I'm going to switch off the surfaces I don't need. Then I'll start with cutting the solid. So I select, go to divide solid, my main solid, tool surfaces, like this. I press OK. So now we have a proper segmental increment of all the solids. So now what I do is I activate all the solids now. So what we do is we go to auto connect, select all, and we press OK. So here you can see the solids have been connected to each other. So if you're unsure if the auto connect has worked or not, what you can do is you can always go select auto connect again, select all, press OK. So I delete the redundant solids. If you don't want to delete them, still not a problem. But what you can do is go to this right view and hide them. Similarly, right view again and hide all of this. So that only the solids that are connected to the main solid in here and the intersections are present. So what I'm going to do is I'm going to activate all the solids. We'll take a look again. So these are the solids that we are interested in right now, these 4 solids, and we don't need the rest. So keeping them apart, we will just deactivate the rest of the solids. Hide, hide. So these 4 solids are left here along with the intersections, like this. Okay. Now we'll start with the meshing. The meshing always starts with the smallest solids. So what we do is go to mesh. Before meshing, we have to start with the creation of the material properties. So for that, go to create isotropic. Drop down menu will be more column, name it as soil, and the properties mostly were like 50 MPa point Poisson ratio 0.2 was there, so we press 0.2 here. Porous is not required because we are not taking groundwater into account. Non-linear 30-36, we press OK. And similarly for concrete, we go to isotropic again. The material model will be elastic. We write it as 2.7 E7, 0.2 unit weight 24. We click on the structure tab. .2 and 24. Press OK. So I hope everyone also remembers how to make the properties. So I'm not going to cover that again. So there is a small part we just need to do to finish the solid modeling. So I again go back to geometry and switch on the grid. So now we just need to make the ground surface. So we go to rectangle, make face. I'm just showing you how to create the rectangle here, but on the tutorial the dimensions will be given. So please ensure that the dimensions are correct for your model too. Otherwise, your results will be very different from what is actually expected from the results. So for now, I'm going to select uh, the extrude option, and this is my target object. Direction being y-axis, length 50 meters. Okay. So all we need to do is just auto connect everything. Go to Boolean, target object, select all, then press OK. So if I gonna make it transparent, you can see the main soil has all the sections incorporated into it. So if I do it like this and hide the main tunnel sections, they're gonna look like this. And I'm gonna make it opaque now. Transparency, opaque, hide. So here you can see the void has been created inside the solid or the main soil for the tunnel and the cross passages like this. So this is how you create the geometry in here. Now I'll just show you briefly how to create the shell element mesh. And then we will go for the creation the construction stages and then the results. So I go to mesh, property, 2D, liner, go to shell, I press liner, property being concrete, thickness being 0.25 meters. Okay. And then I add a new one for the intersection lining, I liner, concrete, shell, 0.5. Okay. Then create 3D for the soil. Okay. Now what we do is I just hide, we just activate all the solids, hide this one, go to front view, hide the cross passages, and then we go to mesh, 3D, select all, go to hybrid mesh, size 1 meters, property soil, we name it as main tunnel. But if I do that, I'll be doing it wrong because this is the bigger mesh set. And remember when I say that we always have to start meshing with the smallest elements. So please keep that in mind that you always have to start your meshing with the smallest mesh sets. That's why I always start with the cross passage. Select all, we name it as TP for cross passage. Press apply. It'll look like this. Now let's activate the rest of the solids. Hide. And go to front view. I just deselect this one and name it as MT of the main tunnel. Apply. So there you have it. Your meshing is complete here. Now all we are left with is the main soil body. So I just activate all the solids again. I take this size as 3 meters, name it as soil. Apply. So this is how you start with the basic geometry from scratch and then go towards the meshing of the solids into its current format, like this. So our geometry and our meshing is complete. So all we need to do now is supply the loading conditions that are the self weight or the gravity loading, and I just name it as SW. Press OK. And in the constraints, we just go to constraint and go for the auto constraints. I name this set as BC or the boundary conditions. I press OK. So here our model is complete. It looks exactly identical to this model, like this. Okay. So this is the basic protocol that you have to follow to create a model, and then we'll go for the creation of the shell elements. So I just switch off the boundary condition and the static load. I also switch off the mesh sets. Instead, I switch on the solids. I'm gonna hide this one up. So the creation of the shell or the plate element will be a bit time-consuming process for you, but that is the best way of doing it. So please ensure that you follow this particular method of creating your shell element. Go to extract. In the type, select face, and this, and we press it and we note it as empty underscore liner underscore one. So similarly, in here, all you need to do is just select the outer edges of the cylinder, and here you rename it. Please remember, when you extract an element, you always have to keep on renaming them. If you don't do it, then it will lead to merger of the freshly created extracted element with the previously created extracted element. So every time you extract the new elements or the new edges, make sure you change the name first before pressing OK, apply. So this is how the liner method can be created, and you can see it's quite easy to follow. So this is how you'll create the methods for the liner. Then we'll go to the creation of the construction stages. So we go to static slope analysis. We go to stage set. The stage type will be stress. We press add and we click here and we go to define construction stage. So here at first we activate all the mesh sets except the ones for the liners. Select drag and drop. But before that, I'm going to just deactivate the geometry and activate the mesh sets. Use the pan option. Activate the, in the show data option, go to activate and then drop the soil in here. Boundary condition, self weight. And since it's the first stage, we name it as IS or the initial stage. And here we activate the clear displacement option and we press save. So next we go for the first stage where we excavate the first part of the first segment of the main tunnel. We press new, we name it as MTEX1. So I just deactivate uh, the method for there, and let's activate the liner. So this is how you can keep on creating your construction stages until the last stage, until the 25th stage, and in the end, just press close. And after this has been done, go to analysis. In the top toolbar, go to analysis tab, click on general. In the solution type, go for construction stage. Name it whatever name you want to give. Then go to the analysis control. Then we activate the K-note condition. So we also activate the cutoff negative effective pressure, and we press OK. And press OK. So there you have it. This is how you can create the model from scratch to the construction stage analysis. So then we just need to run the analysis. So after that, I'll just briefly show you the results of this particular model. So for the first stage, there will be no displacement because we had used the clear displacement option. Similarly, if we look at the stresses in the ground, the horizontal stress, so also the horizontal stress and the vertical stress. Now I just pick up any random stage, go to displacement. This is my total displacement here. Now vertical displacement. If you want to see the displacement along the crown, go to the probe option, and here you have it. And along the walls, like this. And you can also use the vectors to see the direction of movement. Since it's a soil-based tunnel, you can see there is squeezing on that. So this squeezing is nothing but the segmental pressures which are applied to the segments while we design a shield TBM mode. So similarly, if you want to see the displacement results, you can do that. Now we also have this option called as cutting plane option. So let's say there is something you want to see in the middle of the model. For that, just select the clipping plane. And we press add. And here you can see how the interior of the model looks like. And if you want to see the deformed shape, it's going to look like this. In other words, there is squeezing. The top one or squeezing or convergence along the top, top and the bottom, and on the sides there is a divergence. So apart from that, if I just switch off the clipping plane and we want to see the forces acting on the structural elements, so I just go to shell element forces, membrane force. That means I just deactivate the soil so that it's clearly visible. Go to undeformed. It's going to look like this. So this is the horizontal forces, the vertical force, and if I just activate this soil, you can also check for the plasticity in the soil body, go to solid stresses, plastic status. So we have the plastic zone is very less in here, and that is due to the fact that in this model the soil is quite competent. At the same time, the liners have been made very thick. So whether this model qualifies according to you as your project model, it is entirely onto your interpretation. But yeah, this is just an indication of showing that how it can be done. In this model, the liner was thicker than necessary. That's why the subsidence is less. And it, in terms of an engineering and a project based comment, one can say that we have added more concrete than necessary. So this is a good start. Here, what you can do, you can always reduce the thickness of your shell element and then check what kind of deformations you are getting. As long as the model is not diverging and your deformations are in the proper range, you can always use the same model as a benchmark to test what other criteria you want to fulfill in there. So apart from that, we can also get the image file exported to your in an image format or in image format or the Word format. So I'm just going to export this particular thing into the image format, execute, and if I go and select this, so this is how it looks like, the exported image. So I hope everybody here enjoyed the session that we just provided for the 3D construction stage analysis. I understand a lot of you have questions because I assume a lot of you also have prior experience with modeling too. But our main intention behind leaving various forces and interface elements for this session was that we did not want to make it very hard for the user to interpret what we are trying to show. So the same thing, whatever has been shown in this particular session, will be given to you as a certification task, and we don't want to make the certification task very tough for the participants. So that is also one of the reasons why we try to actively avoid the addition of various different kind of forces, the squeezing of the soil layers and the segmental forces, as well as the creation of interfaces. So I hope everybody agrees with our point of view. And if you don't, we still have a lot of other webinars in our YouTube channel that you can take a look at, where various different kind of forces and other elements for various tunneling methods have been utilized properly. So if you have any questions right now about the session that was just about to be concluded, please feel free to write them on the questions panel. I'll try to answer them now. So I'll repeat myself. If you have any questions, please note them down on the questions panel. We'll be happy to answer them. And kindly note that tomorrow you will receive the GTS NX trial license. along with the model files and the tutorial files, and the presentation PPT and the videos provided here will be sent to you via mail, so you can always refer to them. But meanwhile, if you still have any more questions while you are doing the modeling, you can always send us a ticket at globalsupport.bidasuser.com. So before I conclude today's session, I just want to share with you that please remember that the last date for submission will be uh, 21st May, and please submit your report via the link that has been sent to you. And also, I'll just the you will have a questionnaire that you have to fill up, and I will recommend just put the data in there. You don't need to put snapshots where it is not required. Only put snapshots where it is written that we need a snapshot of that particular result. Where it is not required, just put down the data. That should be fine for us. Because in some of the reports that we have received, the resolution was not clear, and it is a very hectic and a time-consuming process for us to actually analyze that particular image and then process it and then try to look for if the user has done the model correctly or not. So kindly ensure that apart from the questions where it is required that you attach a snapshot, don't send us any other snips for the other questions. So if you have any questions now, please feel free to ask on the question panel. I will answer them. Or if you have any request that you want to put on for the upcoming webinars that we will do in the future, you can also note it down. We'll be very happy to acknowledge your request and try to cover it in the future webinar sessions. So if there are no further questions, I'd like to thank you all for attending today's session. And before I closed on, I got a really good question that how hydrostatic pressure and surcharge applied over the model. Actually, here we have not applied any hydrostatic pressure, but if you want to do that, you can just simulate the groundwater level. I'll just show you the easiest way of doing it. I'll just go to the model right away, and I go to the pre-stage. So now what we'll see is that so all we try to do now is just see the location of the ground surface here. So the ground surface is at z-axis 25. So let's say the groundwater has a depth of 5 meters. So what we do there is I just go to analysis. In the initial stage, I just edit that, and here you can see the defined groundwater level. So those of you who had participated in the last webinar and also completed the tutorial task that was given, they will be able to relate to it. So all you need to do here is just put 20 meters. So if I press OK here, save, close, you can see this is where the groundwater has been simulated. So now you can just do your nonlinear static analysis and then you can see that. But if you want to have more closer look at seepage forces, hydrostatic forces directly acting on the tunnel walls, you can just go for a seep and stress coupled analysis, and you will get the results from there. So I'll just repeat and show it to you again. All you need to do is just, if you can see, the top of the model is at the height 25 meters. Just go to the initial stage, and in the previous model we did that. So all you need to do is just put the depth here 20 meters, and that is how you simulate the groundwater level in here. So that will be one way of doing it. But since this is only a non-linear static analysis, you won't get the direct results of the seepage induced forces in there. So to get that, all you need to do is go for a coupled analysis. In this form, a semi-coupled analysis will do the job. You don't need to do a fully coupled analysis. Any other questions, anyone? So for the certification task, all you need to do is just replicate the same model, and you will get the and on the mail you will get what you have to do in there. So I hope everyone enjoyed today's session. On behalf of MIDAS IT, I am Chinmay Patnaik signing off, and thank you very much. And also, I would like to express my gratitude for allowing us to showcase our work in front of you. I hope it was worth your time. So thank you very much, and I wish you all a nice day ahead. And please be safe from the current COVID situation.